All right, this is a lesson about polynomial functions. It's found in our textbook in section 3.2. First, we start with the definition of a polynomial function. And they give us a very specific, well-written definition, but unfortunately tends to be rather confusing for many students. What it is saying is, the function is polynomial if you have terms of x, each with an indicated power, with a coefficient in front of it, and the exponents determine the degrees of the polynomial, and they cannot be negative because that would cause the x to go into the denominator. They cannot be fractions because that would cause you to take roots of the x's. Other than that, this is a polynomial on the right-hand side, and it looks very much like the expressions that we factored earlier in the course. The coefficient of the leading term is the leading coefficient. Now we're going to have a little discussion about what is the behavior of these graphs, and it's going to be determined by, number one, the degree, the highest power, and the sign of the leading coefficient, whether it is positive or negative. So I'm going to push this out of the way and begin to make a chart. I'm going to talk about the degree. I'm going to give an example of the structure. I am going to, give you the shape. And then finally have a discussion about the end behaviors. Let me rewrite that. In other words, what's it doing extremely to the left and extremely to the right? Everything that is in my chart will be assuming that the leading coefficient is positive. So keep that in mind. All right, degree 1. Example, y equals ax plus b. We usually call it mx plus b, but I wanted it to fit with these letters, so I'm calling it a. What is the shape of this? Well, we get a line. If the slope is positive, then it is increasing over its entire domain. And the end behaviors, it is going down on the left, and it is going up on the right. All right, second degree. This is y equals ax squared plus bx plus c, and we just finished a study of these quadratic functions. If the a is positive, then it is opening upward, and its end behaviors are up on the left and up on the right. Third degree. It would look like y equals ax to the third plus bx squared plus cx plus d. Any of those coefficients could be 0 except for a, in order for it to be what is called a cubic function. If the leading coefficient is positive, then it will look kind of like this. And I tend to call those the roller coasters. So this will give me a function which is down on the left and up on the right. If it is fourth degree, you have y equals ax to the fourth plus bx to the third, and I'm just going to put ... because I don't want to keep writing all that, and you will get something. It does not have to be symmetrical, but you will get something that at least sort of looks like a W. And the end behaviors are that it goes up and up. All of this could be verified by examples using your graphing calculator. If it is fifth degree, it is y equals ax to the fifth plus bx to the fourth dot dot dot, and it would look kind of like this. And these are called, these little relative maxes and mins are sometimes called turning points. The end behaviors, on the left it's going down, and on the right it's going up. I think you can see that the higher the degree, the more of those turning points you have. Nevertheless, you can hopefully summarize there's a pattern. When the degree was 1, it was down, up, then up, up, then down, up, then up, up, then down, up. There is a summary that we will look at. I'll go ahead and show it to you right now. The first part is what I've been talking about. If a sub n, which is the leading coefficient, is greater than 0, all of my examples, I said the a was greater than 0. If the degree is odd, it is down on the left, up on the right. But if the degree is even, it's up on the left, up on the right. So you can see the degree is odd, a is positive, down on the left, up on the right. Then it begins to switch, up, up, down, up, up, down, up. I had not discussed, but it is here, if the leading coefficient is negative, you simply get opposite behaviors at the ends. So you will get, instead of down, up, you will get up, down. And here you will get down, down. So I encourage you to remember this top part, and then if the leading coefficient is negative, it flips over. You get a reflection. All right, let's see a little bit more. The author has this as a summary. It's called the leading coefficient test. And it says, as x increases or decreases without bound, that means goes far to the right or far to the left, the graph of the polynomial function eventually rises or falls. So it is showing that if n is odd degree, degree 1, degree 3, degree 5, it's going to go down on the left and up on the right. I'm not sure what's going on in here, but I do know what's happening on the ends. If a is negative, if the leading coefficient is negative, it flips over. If instead the degree is even, then it will always rise on the left and rise on the right. I don't know how many turning points it will have because that depends on the degree, but for all even degrees, the far left and the far right look like this. If the leading coefficient is a negative, then it reflects over. It falls over so that it's going down and down. Since these functions are polynomial functions, we've spent a good bit of time during our course talking about how to factor polynomials. So you can factor polynomial functions. Now, we will talk about the factors of the function, and those have a relationship or tied to the x-intercepts of the graph. These are also called the roots of the polynomial, and they are also called the zeros of, and I guess I could make all of these plural. They might be singular, they might be plural. So we might talk about them when they're part of the function as factors, but graphically these are the x-intercepts, the roots, the zeros. As a quick example, let's look at a quadratic function. So suppose we had f of x is equal to x squared plus 3x plus 2. If I wrote this right-hand side in factored form, that gives me x plus 2 times x plus 1. These x plus 2 and x plus 1 are the factors. If I am looking for x-intercepts, the meaning of x-intercepts is where the graph crosses the x-axis, so f of x is 0. So x plus 2 times x plus 1. When I solve that and I get x is negative 2 or x is negative 1, these are called x-intercepts when we talk about the graph. They are called zeros because they are x values when the function f of x is 0. They are also called the roots. So I will use these three words interchangeably, and please note that they are related to factors. Sometimes the graph, well, it does two different things really as the graph approaches an x-intercept, a 0, or a root. So I want to give you a little information about that. The power of the factor is the multiplicity, that may be a new word, of the 0. Now I'm going to try to explain this through an example. Whoops. All right, I'm sorry. Something tried to open. For an example, if I have f of x, and sometimes I will write y there. What if it equals x plus 4 times x minus 6, quantity squared, times x plus 1 to the third power, times x minus 9 to the fourth power. Now my goodness, the degree of this would be, if I multiplied all this out, I would have an x. The first term in this part would be an x squared. The first term in this part would be an x to the third. The first term in this part, if I multiplied it out, would be an x to the fourth. So I have 7, 9. This is degree 10. That's not really what I'm focused on right now, but I thought I would mention it. So I think you can tell that x equals negative 4 is a 0. X equals positive 6 is a 0. X equals negative 1 is a 0. X equals 9 is a 0. But this new word I've used, multiplicity, it has to do with the power of the factor. So for multiplicity, and I'm going to abbreviate it, the multiplicity here, there's an implied exponent of 1. The multiplicity here is 2. The multiplicity here is 3. The multiplicity here is 4. The multiplicity, and I'll write this down, multiplicity affects the behavior of the graph as it intersects the x-axis. If the multiplicity is odd, meaning the multiplicity is 1 or 3 or 5 or 7 or whatever, the graph passes through, I'm going to abbreviate that, the x-axis. If the multiplicity is even, then it will touch and bounce away. It does not pass through. The greater the odd number, it's still going to pass through, but it's going to flatten out or linger around the x-axis as it passes through. Even does the same thing. It's going to touch and bounce away. If it came from above, it's going to touch and bounce back up. If it is multiplicity 2, then it will look a little different than if it's multiplicity 4. I'm going to discuss that more when we look at examples. There is a summary out of your book that says graphing a polynomial function. Use the leading coefficient test to determine the graph's end behaviors, which will either be up, up, down, down, up, down, down, up. And we have a little chart about that. Find the x-intercepts by setting f of x equal to 0 and solving the resulting polynomial equation. If there is an x-intercept at r, and I go on and I say, remember, k is the multiplicity of root r, factor r, 0 r. If k is even, it touches and turns around. In other words, it bounces away. If k is odd, it crosses, passes through. If k is greater than 1, meaning the multiplicity it gets higher and higher, then it will flatten out near that point. They say after you have figured out the end behaviors, the x-intercepts or zeros or roots, and know what their multiplicity is doing to each of them, then go ahead and find the y-intercept. Use symmetry if you can to help you out a little bit, and then we will talk about turning points in a few minutes. We're going to do much of this, but don't forget that your grapher will help a lot when we do this. All right, so I'm going to go ahead and stop this video, and I will continue with the video actually working example problems.